Hello guys, good afternoon. How was the Chemon test?
So chemistry was very good.
Sorry?
So chemistry was very good.
Just a second, Vikas. Yes, how was the test, Chemon?
So chemistry was very good.
Was it easy or what?
Yes, sir, it was easy. And sir, the electrochemistry questions, many of them were already there in the assignment. So it was sort of like doing the same question again.
Is it?
Yes, sir.
Maybe, but the source was not same actually. Maybe different books have similar kind of questions for me. That's a coincidence. Should not happen actually. But anyways, what is the marks you get in chemistry?
I got 75.
75 out of 100, right?
Yeah.
Overall?
So 191.
190.
191.
Acha. But 191 won't help because you should cross 225 at least. You should be consistent with that. At least 200 plus 210 around. Okay.
Okay.
That depends upon the nature of the questions or whether the paper is tough or easy. Right. It's a good score, but it would be better if you score consistently around 210, 20 like that. Okay.
Okay.
So check your mistakes and then you start working on that. Anyways, so we have finished this thing. The reaction mechanism we have done alkyl, aryl, halide. Okay. So today we are going to start inorganic portion, that is P block elements of group 15. Okay. So 2-3 quick points here. Group 15, group 16, group 17 and 18. They have there are a few properties which are common in these chapters. Okay, like atomic radius down the group increases, ionization enthalpy down the group decreases, like that. Okay, so here in this group 15 element, okay, we'll go accordingly, whatever the reason is there for that particular order, we'll see all those reasons. Okay, but same thing we won't explain again in group 16 and group 17 elements. Yes, if there is some exception, some changes there, we'll discuss that. But like suppose here I told you down the group metallic nature increases. So reason I'll tell you here, the same reason will be there. Okay, so I won't discuss the reasons over there. I'll tell you the order. It is the order, right? If you want, you can write it down. If there is any change or exception, I will mention that. Okay, this is the change we have. You should keep this in mind. Common things we are not going to repeat again in the other groups 16, 17 and so on, right? That is one point we want to know, right? So here in this chapter, guys, the 2-3 things are most important. One is, like I said, the properties, how the order we have different, the compound forms by various elements like hydrides, we have halides, we have oxides are the most important compound we have here, and then oxo acids of phosphorus. Okay, structure based question they ask. These are the 4-5 things we are going to study in this chapter. And like I already said, you have to go through NCRT, plus if you finish NCRT properly, and then you can go through other books like O.P. Tandon or Singage inorganic chemistry. If any book you have, you can go through. Okay, so we are starting with the elements of group 15. Okay, just 1 minute. Okay, so we are going to start with nitrogen family. Group 15. Okay, this elements of group 15, we also call it as nicogen. Okay, PNICOGEN, nicogen. And compounds of these elements of group 15, compounds we call it as niconides. Okay, compounds are niconides. Like you already know, you're not going to have any numerical questions into this. It's just information based. There are some orders for which we have some logic. Okay, but then this chapter is more about the information based. You should know the fact what is happening when, right? What is the order we get under different conditions? Okay, what is the dominating factor which determines the property of these elements or compounds of these elements? Okay, so basically those things you have to memorize, you have to keep in mind. Okay, you will get theoretical questions into this. There's no numerical question possible. Okay, structure based question also they ask, reaction based question also they ask. Okay, I'll tell you how they ask the question, what kind of question they ask. Okay, so nicogen compounds are called niconides. This term is derived from a Greek word that is uh, nicomix. Okay, nicomix means suffocation. Okay, so on inhalation, this elements no you start suffocating if you inhale it. That's why the Greek letter nicomix, from which these elements are called, based on that particular word, these elements are called nicogen. Okay, and the compound that these element forms called niconides. Okay, not that important. So first of all, what are elements we have in this particular group? The elements we have here are nitrogen, phosphorus, arsenic, antimony, and bismuth. Okay, the atomic number of nitrogen, okay, it is 7, then 15, then what?
33,
18 we add, so 33, and then
51,
83. Okay, so the magic number of this group, you see, this difference is 8, this difference is 8, this is, sorry, 18, this is also 18, and this is also 18. So it is 8, 18, 18, and this is 32. So these are the magic number for this group. Okay, if you know these numbers, you can add and you can find out the atomic number of lower elements. Basically, the electronic configuration here, you see, it is 1s2, 2s2, 2p, 3, right? So NS2 NP3 configuration we have. The outermost configuration is what? NS2 NP3. Okay, half filled configuration. So it has some extra stability. Half filled configuration. And since the last electron goes into p subshell, that's why these elements belongs to p block. Okay, for boron you see it is 2s2 2p1. For carbon it is 2s2 2p2. Then nitrogen 2s2 2p3. Oxygen 2s2 2p4. Then 2s2 2p5, and then 2s2 2p6. So there are six different maximum number of electrons present in p subshell is 6. That's why we have 6 different group here, right? 13 to 18, correct? So NH2 NP3 is the outermost general electronic configuration. Similarly, if you write down the electronic configuration for phosphorus, it belongs to third period. So the outermost configuration is 3s2 3p3. Arsenic belongs to fourth period, 4s2 4p3. Here we have fifth period, so 5s2 5p3 and so on. 5p3. Okay. Now you see as you go down the group, right, the electrons are going into higher energy shell from 2 to 3, 3 to 4, 4 to 5. Okay, that's why what we say that as we go down the group, the atomic radius increases. Okay. Down the group you go. So atomic radius increases. Atomic radius increases, ionic radius also increases. Ionic radius also increases. Okay, what is the reason for this? The reason is what? As we go down the group, the electrons are going into higher energy shell, right? 2 to 3, 3 to 4. That's why it is going away from the nucleus, and radius, ionic radius, atomic radius increases. Now, what about ionization energy? Down the group, if you go, ionization
Decreases.
energy decreases
Decrease.
again because the size is increasing. So ionization energy decreases. Ionization energy decreases means tendency to lose electron is increases, right? So next we can write down tendency to lose electron increases. Now when tendency to lose electron increases means what? Means metallic nature increases, because metallic nature is nothing but the tendency to lose electron. So metallic nature increases. Okay, metallic nature increases means electropositive character increases. Elements has more tendency to lose one electron and gains one positive charge on it. So electropositive character increases. These things order you already know, right? One more order you can write down here. As we go down the group, electronegativity decreases. Fine.
So what about hydration enthalpy?
Hydration enthalpy, we'll discuss that. Hydration enthalpy means when you dissolve in water, right? The energy that increases, correct? That releases. That is what you're talking about.
Yes, sir.
We'll see that. We'll see that. So these properties, whatever I have written here, right? Whatever I have written here, these properties are common for all the groups: nitrogen family, oxygen family, halogen family, etc. More or less common. There's no change into this, right? So we are not going to deal with these particular things again and again in coming groups, right? These are common things. You must keep this in mind, and you can relate all these things together. Okay, these are the few properties we have. Next, write down. Yes.
So what about the inert pair effect?
Inert pair effect we'll discuss when it comes, right? It is there in the lower element. Okay, so we'll discuss this in oxidation state.
Yes, sir.
Okay. Right. Next, write down the next property we have: melting point and boiling point. Melting point and boiling point. Write down. Write down. The melting point of the elements of group 15 first increases from nitrogen to arsenic, and then decreases to antimony and bismuth. Right? So order of melting point, you see, melting point, we have an irregular trend over here. This you must remember. Nitrogen, phosphorus, then we have bismuth, antimony, and in the last we have arsenic. This is the order of melting point. Okay. See, melting point, how do we understand the order? Basically, if the element has tendency to form covalent bond, more tendency to form covalent bond, more will be the melting point. Correct? So as you go down the group, the tendency to form covalent bond decreases, right? Covalent bond means number of covalent bonds. Nitrogen phosphorus has more tendency to form covalent bond. Okay, it has 3 electron in the outermost shell, right? And S in the excited state, S electrons can also take part in the reaction and forms just a second, I'm getting a call. It's urgent, I have to pick this up. Okay. Yeah. Okay, so we were talking about melting point, right? So yeah, we were discussing about this irregular trend of melting point here, and the reason is the possibility of forming covalent bond, right? More number of covalent bond, more will be the melting point, correct? If you go down the group, you see in bismuth and antimony, there will be inert pair effect, right? Inert pair effect here. In these two elements, we have this inert pair effect, correct? And because of this effect, the s electrons, the configuration we have ns2np3, ns2np3, this s electron has less tendency to take part in the bonding because of inert pair effect, right? And hence the tendency for these elements to form more number of covalent bond or number of covalent bond decreases, hence their melting point decreases. So as you go down the group, you see till arsenic, the inert pair effect we don't observe, like, so it increases the tendency to form more number of covalent bond, hence melting point increases till arsenic. But after that we have this inert pair effect, so after arsenic it decreases in bismuth and then it decreases in antimony. So we have this order of melting point. The reason you can understand of this irregular trend, that is inert pair effect. Okay, write down this. Due to inert pair effect, bismuth and antimony has less tendency to form covalent bond has less tendency to form covalent bond, and hence melting point decreases. Boiling point order, you see, as we go down the group, the boiling point increases due to increase in atomic size. As atomic size increases, boiling point increases. More heavier atom, more will be the boiling point. But here also we have an exception, and the exception is phosphorus is lesser than to that of nitrogen. After this, it is fine. Right? So this is the exception we have over here. Trend is this only, but in case of nitrogen, it is an exception. Okay.
So why is it inert pair effect?
We have already
observed?
discussed the metallic character of these elements. Okay. So the first two elements, I'll go back and I'll write down here only. The first two elements, that is nitrogen and phosphorus, are non-metals basically. Nitrogen and phosphorus are non-metals. These two are non-metals. Okay. Then arsenic and bismuth is metalloids, and the last one is antimony metalloids, and last one bismuth is metallic in nature. Okay, so metallic character down the group increases, non-metals, then metalloids, and then metals.
So then the order you wrote was ulta, no? You wrote bismuth before antimony in the later slide.
Okay, one more point I'll write down here. Nitrogen, because of its small size, it is the only element It is the only element which can form multiple bond. Multiple bond, or better we'll write down, can form pi bond with its elements. Okay, so nitrogen can show multiple bonds, and triple bond, and we know, right? But phosphorus, arsenic, antimony, and bismuth does not form multiple bond, right? Easy to understand this also, because nitrogen is smaller in size. The orbitals of the two nitrogen atoms are close enough so that lateral overlapping is possible, right? So because of a small size, nitrogen can show multiple bonds. Okay, next write down
So over here you wrote bismuth.
oxidation state. Oxidation state. You see, these elements
So-
shows, yeah.
So in the boiling point, isn't bismuth supposed to come last?
No, this is the order. I have down the group. If you go, oh, I have written it other way, no?
Yes, so
Oh, yeah, yeah, yeah.
previous
By
slide you had
mistake,
written
yeah.
antimony.
By mistake, I have written this. This is like this. You were talking what? Because the earphone,
Yes, sir.
the earphone was down actually. I realized it later. So yeah, we have this first, and then we have this. By mistake, I have written.
So why is an inert pair effect observed here? The boiling
What?
point.
No, you see, like I already said that we do not have only one factor. Okay, there are multiple factors. So boiling point is basically because of the size of the atom. Heavier atom, its boiling point is more, right?
Yes, sir.
So here the size or the mass of the atom plays a dominant role over here. That's why the boiling point increases down the group. It is common for all the elements actually. Down the group, if you go, boiling point increases. When you have compounds, then we can talk about the sharing of electrons or bonding of electrons there. We'll discuss that in case of hydrides and all, how the boiling points and melting point changes of the hydrides of these elements. Okay, there we'll talk about the state, solid, liquid, and we'll understand this. But here simply what happens, melting point is basically because of the packing of atoms. Okay, we'll discuss in solid state also. If the atoms are a close packing structure, right, their melting point will be more, right? Geometrical isomers also, if you remember, trans isomers have higher melting point. Why is that so? Because trans isomers can show better packing than cis, right?
Yes, sir.
So that's why it has more. So basically the elements, boiling point and melting point we'll talk about. Melting point is mainly because of the crystal of that particular element. Okay, how the atoms are arranged in its crystal, right? Boiling point is mainly because of the atomic size. Heavier the atom, more will be the boiling point. Okay.
Yeah. Yes, sir.
Oxidation state, you see, we all know these elements shows variable oxidation state, right? So the outermost configuration that we have, it is NH2NP3, right? So if I draw this diagram here, orbital diagram, S orbital has 2 electron and D has 1, 2, 3, 4, and 5, 1 and 2. So NH2NP3 is this, right? So the variation in oxidation state is what? First of all, it can mainly show +3 or +5 oxidation state. When these 3 electrons it donates, it shows +3. When all the 5 electrons, this is the ground state configuration, right? In excited state, what happens? S will have 1, P will have 3, and 1 electron from S jumps into into d orbital, right? So when these 5 electrons takes part in the bonding, it shows +5 oxidation state. So in the ground state, it can show +3. In excited state, it can show +5. Remember again, this +5 is possible only when the atom has d orbital. Yes or no? If d orbital is not there, this electron won't be able to jump into the higher energy state, and hence the +5 oxidation state is not possible, right? So nitrogen atom, if you see nitrogen, it does not have d orbitals, right? Nitrogen does not have d orbital, hence this does not show +5 oxidation state. +5 oxidation state is not possible for nitrogen. That's why if you have studied little bit of inorganic chemistry, it is written there that nitrogen does not form pentahalides, right? Nitrogen does not form pentahalides because +5 oxidation state for nitrogen is not possible. Okay, but we have +3 is very common. +5 is also possible for phosphorus and other elements, not for nitrogen. Okay, apart from this, there are different oxidation states also possible. Common one is these things, +3 +5, but it's not like only +3 +5 is only possible. Depends upon the bonding and structure. There are other oxidation state also possible. Like if you talk about one possibility here, that it has 3 electrons in the outermost shell, unpaired electrons, and if it wants to get stability, so either what happens, either it can lose these 3 electron and gains the stable configuration, or it accepts 3 electron and makes all the electrons paired, right? So when it loses, shows +3. When it accepts, shows -3. One here, one here, one here, shows -3. So -3 oxidation state also possible for these elements, right? -2 also possible. Okay, so there are a few examples we'll see next here. First of all, 2 points write down here. The elements of this group shows +3 or +5 oxidation state. Shows +3 or +5 oxidation state. Next point, nitrogen does not show pentavalency because of unavailability of d orbital. Okay. Next point, as we go down the group, the stability of +3 oxidation state increases. The stability of +3 oxidation state decreases, and that of +5 oxidation state, sorry, the stability of +3 increases and that of +5 decreases. Why the stability of +5 oxidation state decreases down the group?
So inert pair effect.
Again, inert pair effect, right? Because +5 only possible when s electrons take part into the bonding, right? And as we go down the group, due to inert pair effect, s electrons becomes inert, right? And hence the stability of +5 decreases down the group. Okay, few examples you see here. What is the oxidation state of nitrogen in NH3? NH3, what is the oxidation state of nitrogen? NH2, NH2. The oxidation state of nitrogen. Similarly, we can have diphosphine. Okay, nitrogen can also show -1 oxidation state in this compound. Okay, like you see in NH3, the oxidation is the hydrogen is +1, so nitrogen is -3. NH2, NH2, what is the oxidation state here? Yes. See, NH2, NH2 overall we can say it has -2 oxidation state, right? But if they ask you this question, yes, if they ask you this question that what is the oxidation state of each nitrogen atom here, then the answer will be what? It is hydrogen, it is NH2 plus and NH2 minus. This kind of bonding we have. So this one is +1 and this one is +3, -3. Is it right? No, -1 and minus. Just a second. Hydrogen is plus. So nitrogen here is -1 and here nitrogen is -3. So -2 is the average, but oxidation state of each nitrogen atom is -1 and -3. NH2OH, OH is -1, this is +1, so nitrogen is -1 over here. So in NH2OH, it is hydroxylamine, right? It is -1, NH2, NH2 -2, NH3, it is -3 oxidation state. Okay. Now we'll see the various compounds of these elements, compounds and their properties. Write down. Compounds and their properties. Okay. The first one we have hydrides. Hydrides. Write down the elements of this group, elements of group 15 forms hydrides of forms hydrides of NH3 type, right? So hydrides of the elements of group 15 is MH3. Like for example, we have NH3 ammonia, PH3 phosphine. These two are only important. One more thing you remember, in all these groups, all these P block, like the content that we have, syllabus that we have, we only discuss about the first two elements mainly, mostly about the first elements, few compounds of second elements also. Like in this chapter, you see NH3 PH3 is important, ASH3 also possible, SBH3 also possible, BiH3 also possible. But the important one is this two. So we'll see the preparation of these two also, preparation and properties. But first, before going into this NH3 and PH3, first we'll see the overall properties of these hydrides and some important order over here. Okay, so the oxidation state of these hydrides, you see the central element of these hydrides, the oxidation state is -3, we have already discussed, right? Oxidation state is -3. The structure, if you see, could you tell me the structure of NH3?
Pyramidal.
Tetrahedron.
Geometry is tetrahedral.
Yeah, geometry is tetrahedral.
John.
Shape is pyramidal.
Pyramidal, correct. So I'll write down the general thing over here, MH3, right? M, and there is one lone pair, okay, and 3 hydrogen attached to it. Bond angle is lesser than 109°28', okay, and this bond angle is coming out to be 107° for nitrogen. It depends what groups we have, okay. So I am not writing down here the exact bond angle, but this bond angle is lesser than the expected bond angle according to the geometry of this molecule, that is 109°28'. bond angle is lesser than this. Okay, the hybridization of the central element here is sp3. We all know this. Hence, bond angle is lesser than this because of lone pair bond pair repulsion. Because of the lone pair bond pair repulsion. Got it?
Hello.
Okay, sp3 hybridization it is. Okay, you can easily understand the bonding over here. We have 3 unpaired electron and this lone pair is present in the s orbital of the element, nitrogen, phosphorus, arsenic, whatever it is, because we know ns2 np3 configuration we have. So 3 electrons present over here, 1 2 3. Okay, and 1 electron of hydrogen shares with this electron, this electron, this electron, and forms the bonding, right? So it is sp3 hybridized orbital which overlaps with the s orbital of hydrogen and forms a covalent bond. So this bond forms, in fact, all these 3 bond forms by the overlap of sp3 and s orbital. sp3 is the hybrid orbital of the element and s atomic orbital of hydrogen. Okay, now we'll see few properties of these hydrides. Okay, so first thing you write down, yes, Advik, 109 degree 28 minute. The first property you write down, bond angle. Write down, as we go down the group, the bond angle decreases. As we go down the group, bond angle decreases.
So I have a doubt.
Bond angle decreases as we go down the group. Okay, so yeah.
So in like NH3, the bond angle is 107. After that, all bond angles are like 90, 93. Why is there
90s,
like
yes.
a drop like that? So why is there like a drop from N in
I'm
all?
explaining that. Wait. See, first of all, bond angle we can find out from VSE PR theory, correct? Valence shell electron pair repulsion theory. That is the theory behind this. Okay, but how do we, get this? This. What is the logic behind this? Okay, theoretically, how do we find out the order? Obviously, the exact value of bond angle you cannot find out theoretically. Okay, but logic you can understand the order over here. So first of all, I'll write down the bond angle here. We have NH3, then we have PH3, ASH3, SBH3, and BIH3. Okay, the value of bond angle you see here. For nitrogen, it is 107 degree, 107.5 approximately, right? 0.5 degree. Then PH3, it is 93.5 degree approximately. Then it is 91.8 degree approximately, 91.3 degree, and then we have 90 degree. Obviously, these values you cannot remember. We usually remember for NH3 because we have seen this particular molecule many times. And you don't have to memorize these bond angles. Okay. So you see, as we go down the group, bond angle decreases. Now the thing is, why this bond angle decreases as we go down the group? Okay. So for this, one thing you can keep in mind, that as the electronegativity of central atom decreases, bond angle decreases, right? As the electronegativity of central atom increases, bond angle increases, electronegativity of central atom decreases, bond angle decreases. Try to understand this. Suppose we have, I'm taking the example of NH3 and PS3. What happens in this, you see? NH3, we have one lone pair and 3 bond pair like this. 1, 2, and 3, correct? Similar thing we have for PS3. Okay, one lone pair. Now, when the electronegativity of central atom is high, what happens with this? This will drag the bond pair of electron towards this side. Yes or no? Like this. Means this bond pair will be shifted towards the more electronegative atom. Here also it will shift, but that shifting is little lesser than the nitrogen one, because nitrogen is more electronegative. So here you see, as you go towards the central atom, okay, as this shared pair of electron goes towards the central atom, so obviously the distance between the bond pair of electron decreases, right? It is converging onto a point. Can we say that, guys? And this tendency will be more when the electronegativity of central atom is more. Yes or no? So since the pair of electron is converging on the central atom, right, the distance among this electron pair decreases. Hence what happens here, we'll have more repulsion as the electron pair are pretty close here because of high electronegativity. So more repulsion means it will expand and bond angle increases. Yes, Richard, that's correct. Did you get it, all of you? More closer, more repulsion, and then to minimize the repulsion, there will be expansion here, right? These two bond pair will go as far as possible, and hence the bond angle increases. So what we can say, as the electronegativity of central atom increases, bond angle increases. As the electronegativity of central atom decreases, bond angle decreases. Hence the order is this. Clear?
Yes, sir.
Okay. Next. Melting point and boiling point. This order is very important. Melting point, boiling point are very important. Okay. So melting point order, you see, first of all, the melting point order for hydrides of these elements, the melting point is maximum for NH3. Then we have BiH3. Wherever you have irregular trend, okay, those orders are very important. Okay, for exam point of view. SbH3, AsH3, and in the last we have pH3. This is the melting point. Okay. Why the melting point of nitrogen, hydrides of nitrogen is highest over here? See, there are two
hydrogen
factors.
bonding.
Hydrogen bonding,
Yeah,
correct.
Hydrogen bond.
Yes, yes. So there are two factors here. One factor is van der Waals forces. One factor is van der Waals forces. And this you can generalize this and keep in mind. Okay, van der Waals forces, and other one is hydrogen bonding, intermolecular H bonding. So when you're talking about melting point, it means we have conversion of solid into liquid. Melting point means solid to liquid conversion. So in solid state, what happens? In solid state, the van der Waals force is not that strong, right? write down this point. In solid state, the van der Waals forces are not so strong, as they are in liquid state.
Sir, can you repeat that once?
In solid state, the van der Waals forces are not so strong, as they are in liquid state. Right? Hence, as we go down the group, melting point increases, due to increase in covalent character. Right? So as we go down the group, melting point increases. But we have an exception. An exception is NH3. Right? So usually what we can say, as we go down the group, the melting point of these hydrides increases because of more covalent character, with the exception of NH3. So that term you must mention, with the exception of NH3. Okay, in the last you write down. Why NH3 we have maximum melting point? Because we are talking about solid to liquid phase, right? So in solid phase, the hydrogen bonding is strong, right? In fact, it is stronger than the hydrogen bonding in liquid or gaseous state. That's why in case of NH3, intermolecular hydrogen bonding plays an important role over here, and it dominates the other factors. That's why NH3 exceptionally have maximum melting point, and after this, from phosphorus to bismuth, it increases, right? So order is this for melting point. Right, so what is the one general thing that I told you is what? In solid state, intermolecular hydrogen bonding is stronger than liquid and gaseous state, right? And for van der Waals force, it is ulta, right? Van der Waals force in solid state, it is not that strong. Okay, it is more strong in liquid or gaseous state, right? So these two factors actually defines the melting point order and boiling point order. Okay. Similarly, if you write down the order of boiling point, write down boiling point order is, again we have an irregular trend over here. We have BiH3 maximum, then we have SbH3, and here we have NH3, and then AsH3, and then pH3. So phosphine has minimum boiling point here. The reason is we are talking about the boiling point to liquid to gas conversion you have, right? In liquid phase, the hydrogen bonding is not that strong, right? But van der Waals force is strong over there. So the overall order is because of the combination of the two. So van der Waals force is stronger for BiH3. Hence, for BiH3, we have maximum boiling point, right? But intermolecular hydrogen bonding NH3 shows over there, right? But it is not that strong as it is compared in the solid state here. That's why it comes out to be somewhere in between these elements, right? So we have an irregular trend over here. You can write down the reason for this is van der Waals force strong van der Waals force for in BiH3? Right, van der Waals force, you can say in some book they have written molecular mass also. If molecular mass increases, then also boiling point increases. Right, so NH3, obviously in NH3 we cannot neglect the hydrogen bonding. Right, it's a relative thing that in solid state hydrogen bonding is strong. Right, in liquid state also it shows. Right, but the molecular mass of BiH3 is higher than to that of NH3. That is for sure correct. Right, so molecular mass slightly dominates the hydrogen bonding tendency. Right, so that's why for Bi and Sb the boiling point is slightly more than to that of NH3. Right, these two will have higher molecular mass, but these mass over here is not capable of dominating the hydrogen bonding nature over here. Right, that's why the overall order is coming out to be this. Done. Okay, now thermal stability. We know as we go down the group, bond length increases and hence thermal stability decreases. So third point you write down, thermal stability. Thermal stability means stability towards heat. Thermal stability decreases down the group as bond length increases. It's a regular trend we have. NH3 is maximum, then PH3, ASH3 and so on. Thermal stability order is this. Okay, next. Reducing agent. Reducing agent means what? Tendency to lose hydride ion. Okay, hydrogen is the reducing agent. Now as we go down the group, thermal stability decreases, means tendency to lose hydrogen will be more. Hence what we say, as we go down the group, the reducing tendency increases. Write down. The reducing tendency of these elements means the hydrides of group 15 of these elements increases down the group, since the thermal stability decreases.
So could you repeat it?
The reducing tendency of hydrides of these elements increases down the group as thermal stability decreases. Okay, so which one is the strongest reducing agent?
BIS.
Right, BIS, it increases down the group. Next one, write down basic character. We are looking at the properties of it. Okay, preparation of NH3, preparation and properties of NH3, specific NH3 and PH3 we'll see after this. Basic character, write down. Could you tell me, like basic, you know the reason behind this, which one is the strongest base? NH3, PH3, ASH3, etc.
So is it NHC the strongest base?
Why NH3 is the strongest base?
So it won't give out the hydrogen very easily because of this thermistor with your. And if you give hydrogen,
Second point is what? We can also define this as Lewis base nature, right? NH3 has smallest size, nitrogen, right? And this electron density here, it is maximum. And hence it can donate this electron pair easily because electron density is maximum. As we go down, size increases, electron density decreases. Electron density decreases means tendency to lose electron is less. And hence the basic character decreases. Okay. So these are the few properties we have for hydrides of group 15, elements of group 15. Okay. Now write down the most important hydrides of group 15, that is ammonia, NH3. Preparation methods of ammonia, properties you must have to memorize. Okay, there is no other way, no logic you can put in, right? So that you can understand this. How do we prepare this? What are the methods we have that you have to memorize? Write down ammonia. Okay. It is prepared by heating ammonium salt with caustic soda or lime. Okay, reaction you see. NH4Cl plus NaCaOH whole twice. NH4Cl plus CaOH whole twice. It gives NH3 plus H2O plus CaCl2. This is the reaction we have. Okay. Laboratory method of preparation. We have again we have the same reaction, NH4Cl. So we'll take here slaked lime, that is CaOH whole twice. Again, it's the same reaction actually. NH3 plus H2O plus CaCl2. I am not writing down the balanced reaction here. This is again the same reaction. We are heating it. Okay. You can take other salt of ammonia also. You can take NH4 whole twice SO4. Right. Another method of preparation we have, and this one is important. Okay. By action of water on metal nitrides. Okay, so you see this reaction here. We have magnesium nitride, that is Mg3N2 plus water dissolved in water. It forms what? Hydroxide, MgOH whole twice, and ammonia it forms, NH3. So metal nitrides also we can use for this purpose. right? This ammonia that you get here, this is the moist ammonia. There will be some moisture present into this, okay? And this moisture we can remove with the help of quicklime, okay, CaO. So CaO, when we allow to pass through this mixture, it takes this moisture and forms CaOH whole twice. So this quicklime CaO we use to remove moisture from ammonia in this method. Important, this information also. Okay. There is one very
So-
important, yeah.
So is there any difference in the product of those two, lab method and the first reaction?
No, there's not any difference. Okay, it's the same reaction actually.
So then why do we have to like heat it? Like without heating it, only you get
Yeah,
it.
this is also fine. This mixture you have to heat it. Actually, it's the same thing. I wanted to give you another reaction here. I have written it, so I did not remove it. Okay, like I told you, no, we can take sulfate of ammonia also, NH4 whole twice SO4 plus NaOH. That also gives you ammonia. There are many different methods. Okay.
Yes,
See,
sir.
lab method we use, which is the most efficient way, in which the risk factor is minimum, right, and cost efficient also,
Yes, sir.
right? We have another various reactions which gives you ammonia, right? The another one we are going to discuss now, N2 plus H2 gives NH3, right? But the lab method is the one which is cost effective plus with minimum risk. Okay, those kind of methods we use in the lab. Industrial scale, what happens there, the major factor is what, the process, the entire process must be cost effective, right? There is no point of obtaining a product at very high cost which you cannot sell in the market, right? So on the industrial scale, the method may not be different from the lab method, okay, because there the priority is different. Here in the lab the priority is different. In the lab it is just for testing, right? What methods gives you pure compound, how risk the entire method is, right? What all things you have to keep in mind, like what amount of money you have to put in to get those products. Okay, the entire thing we analyze in the lab. Okay, and based on all these factors, the one which is the most like the most favorite method is what, which stands on all these categories properly. Okay, must be cost effective, must be minimum risk, other things, right? So those kind of methods we have. Yes, there are different methods, but lab method is the one in which we'll get, you can say NH3 here is the the purity will be more. That is also one of the methods. Another method, if you write down, like for example, NH4 whole twice SO4 plus NaOH, that also gives you NH3. But that is not the laboratory method. Maybe the purity of ammonia is less over there. So all these things, why this one is lab method, why that one is not, all these things are not written in the book. So possible reason is what? These are the possible reasons that I'm telling you. Okay.
Yes, sir.
Yeah. So this is the method. Okay. One important one is this metal nitrides. Why lab method we discuss here? Because sometimes they ask this question directly in the exam. How do we prepare ammonia in the lab? They'll mention this. You should know what is a lab method. Okay. In fact, in all the compounds you see, mostly almost all the compounds, they have written laboratory preparation method is this. Right. So that's why you need to know this. Correct. Now another method of preparation, manufacturing of ammonia. Now you see this is the manufacturing of ammonia. Like in industry we use this method. On commercial scale we use this method which we are going to see now. Okay, just a second. So is it NH3? Yeah, it is. We are discussing NH3, Azik. Fine. So commercial scale or manufacturing of ammonia is done by Haber's process. You must have heard this name, right? Haber's process. In this process, what happens? N2 reacts with H2 and gives NH3. This reaction is reversible. 2NH3 and 3H2. Right? This reaction is reversible, right? And according to Le Chatelier's principle, the favorable condition for this is, the favorable condition here is, the first one is low temperature and the second one is high pressure. So these conditions also they may ask you. High pressure. The enthalpy of this reaction delta H is less than 0. It's negative. I didn't get you, Advik. Okay, pressure is 200 atmosphere. Yeah, pressure is 200 atmospheric, but you don't have to memorize those, values, that what pressure we use and other things, right? We can also use some catalyst over here, right? What are catalysts we use for this process? No idea? See, we can use catalyst of elements of certain elements oxide. Actually, we can use. We can use Al2O3. We can use for this purpose, right? Catalyst. I'll write down here. Catalyst used. We can also use iron Fe as a catalyst. Al2O3, Fe, K2O also we can use. Promoter is molybdenum. We are using for this reaction. I said that we are doing. Oh yeah, I got it, Advik. Fine, understood.
So what does a promoter do?
Promoter actually, it you can say it just what we can say, just initiate or promotes the reaction. Catalyst is different. Catalyst is what which enhances the rate of the reaction, right? Promoter is what which helps the reaction to start. Once the reaction is start, then the promoter role is over there.
Yes, sir. Thank you.
Right? The catalyst help here. The only one possibility for catalyst we have, like we know this factor. There are two types of catalyst, right? Positive catalyst and negative catalyst. Correct? So mostly in our syllabus, we have to deal with positive catalyst only. Even if catalyst is written, it means it is positive catalyst. So catalyst things we have discussed, no, it decreases the activation energy. Means suppose this is the product we have. So if catalyst we use, so this activation energy, this energy decreases, so that the reaction goes with a faster rate like this. So this is the activation energy from here to here in presence of catalyst. Without catalyst, the activation energy was this. Yes. So actually what happens when catalyst, in presence of catalyst, the reactant molecules start colliding with each other with a very faster rate. Means the frequency of collision increases, right? And hence what happens, the energy of the reactant molecule increases, which helps the reaction to proceed towards the product in a very lesser time, because relatively if you see, the reactant molecule is at higher energy, so activation energy also decreases, right? It increases the energy of both product and reactant, right? So that the net value of activation energy decreases. So basically answer to your question is the frequency of collision among the reactant molecules increases a lot in presence of catalyst, right? That's why it can, cross that energy barrier, that activation energy barrier easily in a lesser time. Hence the reaction becomes fast. Okay, that is not, the portion we have here. Right, so catalyst is iron Al2O3, molybdenum is the promoter, low temperature, high pressure we use for this reaction, and all these conditions they have asked in the exam. Okay, temperature relation, pressure relation they have asked in the exam. correct? We know the geometry, we know the shape of these molecule, that is NH3. That is, no, we don't have to discuss here. Another thing you write down, the properties of ammonia. It is, quickly you write down 2-3 points. It is a colorless gas. Can be easily liquefiable. Can be easily liquefied, sorry, can be easily liquefied at room temperature. Can be easily liquefied at room temperature. And remember, if you remember this, we have discussed this liquefaction of gas in states of matter. There we have understood that when the interaction is more, liquefaction is easier, right, of the gaseous molecules. So A value of the van der Waals parameter that you have, A. So A value of NH3 is high. That's why its interaction is more and it is equally and it is easily liquefied. Okay, that is the reason behind this. Okay, so easily liquefiable at room temperature. Okay, write down. It behaves as a Lewis base due to presence of a lone pair on nitrogen atom. Behaves as a Lewis base. Okay, write down. It reacts with sodium hypochlorite, NaOCl. Right, it reacts with sodium hypochlorite and forms hydrazine. I'll show you this reaction, and forms hydrazine. Reaction actually takes place in two steps and we'll take excess of ammonia for this reaction. So we have NH3 reacts with NaOCl, forms NH2Cl plus NaOH. This step NH3 is in excess. Now in the next step we call it as chloramine because NH3 is amine, Cl is present, so chloramine it is, right? So chloramine NH2Cl again reacts with NH3 since it is present in excess. HCl goes out and it forms NH2, that is hydrazine. So this is the reaction we have. Now one important reaction of this hydrazine is what? It reacts with ammonium chloride. In this only you write down. NH4Cl reacts with NH2 and it evolves nitrogen gas, N2. NH4 plus Cl minus we get. Okay, so nitrogen we obtain from hydrazine also by this reaction. Okay, write down ammonia on oxidation gives nitric oxide. This question they have asked in the exam, that which oxide of nitrogen is formed on oxidation of ammonia. Okay, so ammonia on oxidation gives nitric oxide NH3 plus O2 in presence of platinum, the catalyst. It gives NO, this is nitric oxide, and water molecule H2. And we'll see this oxides of nitrogen also in this chapter. Nitrogen forms various different types of oxides. It is N2O, NO, NO2, N2O4, N2O5, N2O3. There are different oxides of nitrogen possible, right? So that's why they ask this question many times, that in which reaction what oxides of nitrogen obtained. So oxidation of ammonia gives you nitric oxide, right? So these are the few reactions which is important, okay, and you must keep this in mind. Okay, next write down phosphine. Phosphine is pH 3. Okay, preparation of phosphine, the preparation method will be seen. Write down by hydrolysis of metal phosphides by hydrolysis of metal phosphides. For example, you see calcium phosphide Ca3P2 with H2O. It gives CaOH whole twice plus pH 3. Okay. Hydrolysis, even if you take this calcium phosphide with dilute HCl, means hydrolysis is possible. The another method is the reaction with dilute HCl. It gives CaCl2 plus pH 3. So by hydrolysis or by reaction with dilute acid, calcium phosphide gives phosphine. Okay.
So could you go back to the previous slide for a second?
Just a second. Lab method we'll see next.
Yes, sir, done.
Lab method you write down. In lab, it is prepared by heating white phosphorus. White phosphorus is one of the allotrope of phosphorus. Okay, we'll see that later in phosphorus. Okay, it is prepared by heating white phosphorus with concentrated NaOH solution white phosphorus with concentrated NaOH solution in an inert atmosphere of CO2. So it forms pH 3 and we get sodium hypophosphite NaH2PO2. This sodium hypophosphite is this. This on heating, it converts into Na3PO4 and again phosphine gas evolves into this. So this is sodium hypophosphite. And this is sodium phosphate.
So
Inert
what was
as
the atmosphere?
yes,
So what was the atmosphere of?
CO2, carbon dioxide we are using.
Okay, sir.
Inert as for atmosphere means what? Means whatever gas we are using here, right? That should not react with any of the reactant molecule. Like suppose if uh, and we provide that temperature and pressure, the condition of the reaction is such that CO2 won't get dissolved into this solution, that is water or NaOH, whatever it is present, right? So we are taking this reaction in presence of CO2 inert atmosphere. Okay, so laboratory preparation method is this. We are using white phosphorus. This question they have asked many times in the exam, that for lab preparation, which phosphorus we use, white phosphorus, yellow phosphorus, red phosphorus. These are the allotrope of phosphorus. We'll discuss that later in phosphorus section, right? Next, you write down pure phosphine pH 3 is pure phosphine is non-inflammable, but in presence of P2H6 phosphorus dihydride, it P2H6, it is present as impurity. Whenever you prepare this pH 3, P2H6 present as impurities there. So in presence of P2H6, it becomes okay. So this property we'll use this property of this impurities in a purpose that we call it as Holmes signal. We'll discuss that now, just a few minutes. Okay, so P2H6 is an impurity and then it becomes inflammable, right? Property, write down, it is a colorless gas, highly poisonous, soluble in water, okay, colorless gas, highly poisonous, soluble in water.
So for which one this is?
Properties of pH 3. Okay, colorless gas, slightly soluble in water, highly poisonous, and its aqueous solution is neutral. And its aqueous solution is neutral. Next point, on heating, in absence of air, it decomposes into its constituent element, that is phosphorus and hydrogen, in absence of air. Next, write down, it is used in Holmes signal. What is Holmes signal? I'll tell you. Holmes signal. This actually used by the shipping industry, this naval industry that we have, basically by the Navy, okay, to send signal to the other ship, okay, friendly ship that we have. So what happens in this Holmes signal, actually, there's a box, okay, and in the box we have a mixture of calcium carbide and calcium phosphide. It is present into this, okay, CaC2 and Ca3P2 present into this. Calcium carbide and calcium phosphide, Ca3P2, is present into this box. And there's an arrangement of, you can make a hole into this. There are two arrangements, you can make a hole into this, like this. So whenever the ship or anything, if it needs any help deep into the sea, right, so what they do, they throw this, they make hole into this box, and then they throw this box into the sea, right? When water enters into this box through this hole, right, then the reaction takes place between water and this mixture, okay, and this reaction gives you the evolution of pH3. From this mixture plus H2O, it forms phosphine gas and acetylene, right? So this, on when water enters into this mixture, it forms acetylene. I'm not writing down the complete reaction, plus pH3. Now this pH3 is not pure over here. It is poisoned with P2H4, phosphorus dihydride. Right? It is poisoned with P2H4 phosphorus dihydride, right? And this is, in presence of this impurities, this catches fire. This is inflammable, right? This acetylene, we know it gives what we can say. This acetylene gives this acetylene, we can say it gives we can say spark or brightness. We can say it provides brightness, right? And when in presence of this P2H4 as impurities, it catches fire with atmospheric oxygen, right? So with this fire, there is a small explosion. It won't harm the ship actually, but there will be a small explosion, and we have light because of this acetylene, and this is considered as a signal for any help in case of any emergency, right? So this is used for the by the naval industry. All the navy of all countries, they use this kind of thing to produce, to send signal to their friendly ship, okay, in case of any emergency and all. So we call it as Holmes signal. Sometimes they ask this question, what is Holmes signal? So it is a mixture of calcium carbide and calcium phosphide. How it produces signal over here, we make the hole into this, throw into the water, and water enters into this, the reaction takes place, forms acetylene, provides brightness, and this pH3 is impure, so it catches fire with atmospheric oxygen, there will be a small explosion, and that is considered as a signal. Okay, the Advik is asking, pH3 is poisonous, won't it kill all the fish nearby? Okay, so that's an interesting question. Okay, first time I have I'm experiencing this kind of questions, okay, in my entire 6-7 years of experience. But anyways, a correct question, Advik. But there's a term, there's a English word called priorities. Okay, if you want to save your life, first you'll save your life. Okay, after that you'll see consider fish and other aquatic animals. Right? Humans are the most prioritized animal on the earth. No. So when it comes to human life, everything Every other thing is on the second priority. Right, Advik? Yes, so that's the thing. Your question is genuine. It may harm the aquatic animals, fish nearby, but in that case, you do not have any choice. You have to go for that. Okay? Right. So this is the home signal, important one. This particular thing is important. In NEET, they have asked this question many times. Okay, many times they have asked this question in NEET and other exam. Okay, so this mixture is important. Okay. Sometimes they ask this question also, what is the reason why pH3 catches fire here? So it is because of the presence of impurities, which is phosphorus dihydride. This question also they have asked for. Okay, so these are the few preparation methods of phosphine and properties. Okay, the next thing we have discussed, hydrides. Okay, various different properties of hydrides we have discussed. Correct. Next, to write down the other type of compounds these elements forms, and this is oxides. Okay, write down formation of oxide. The second type of compound we have oxide formation. Few important points to write down here. See, as we know, when you go left to right in a periodic table, right, the metallic nature decreases. S block elements are metals, then metalloids, and then non-metals. P block side, right side of the periodic table, right? First point to write down, oxides of non-metals are acidic. Oxides of non-metals are acidic, comma, those of metalloids are amphoteric. Those of metalloids are amphoteric, and those of metals are basic. Okay, if you have an oxide, so the element that is present over there, one of the elements is already we know it is oxygen. The other elements, if the electronegativity difference between the two elements is more, they are more acidic in nature. More electronegativity difference of the oxides, more acidic the compound is. Correct? Write down. Greater the electronegativity of the element, more acidic the oxide. This point, the third one is very important, write down. Among the elements of same oxides, sorry, among the, wait, just a second, N2, N25, right? Okay, write down. If the element forms more than one type of oxides, if the element forms more than one type of oxides, then the acidic nature of these oxides, depends upon the percentage oxygen character. Acidic strength of these oxides depends upon percentage oxygen character. Yeah.
Sir, can you repeat the first point again? I disconnected.
Oxides of non-metals are acidic. Those of metalloids are amphoteric, and metals are basic. Right? Yes. If you have oxides of same element, for example, nitrogen forms various different types of oxide, N2O, then NO, then we have N2O3, N2O4, N2O5, etc. So when we have elements, oxides of same element, then as percentage oxygen character increases, acidity of this oxide increases. So acidic order is this. Acidity increases over here. This particular information is very, very important. Many times they have asked question on this. Among the oxides of same element, if you have to compare. Okay. Reason is as percentage oxygen character increases, more percentage oxygen character, more acidic the compound is. Because more will be the electronegativity difference.
So if the percentage is same,
then you won't get the same percentage, because when the two elements combines, if the percentage is same, it means the molecules are same, right?
so like if NO2,
NO2, right? NO2 I haven't written here, no? NO2. NO2 percentage oxygen character is what? Could you tell me?
66.
Is it what? Here you tell me percentage. Here percentage of oxygen character is what? It is 33%, correct? And here it is 66%. Here it is 50%. And similarly, you can find out here. Obviously, when it is same, then you cannot say that. Suppose you have two different elements, right? SO2 and NO2. You cannot compare percentage oxygen character here, because these are the two different oxides of two different elements. Percentage oxygen character we use only when we have oxides of same element. So you cannot have two different molecules with same percentage oxygen character of the same element present into this.
Sir, but what about NO2 and NO2O4?
NO2O4.
N2O4, I think.
Sorry,
N2O4.
N2O4.
N2O4 is the dimer of it actually. It is the dimer of it. So in this two you cannot compare. But if you have to compare in this one, right, then this will have more oxygen. So this is slightly more acidic than this. But the difference is not that great. N2O4 is actually the dimer of NO2.
Okay, sir.
Okay, we'll discuss this. Oxides, we'll discuss this. Okay. And that is why I haven't written here NO2. Okay. So if you have the oxides of same elements, just compare percentage oxygen character, you will get the acidity. Okay. Two types of oxides generally these elements forms of group 15. One is trioxide. Write down. One is trioxide, and other one is pentaoxide. The acidic strength of trioxide, you see, it follows this order. Down the group you go, electronegativity decreases and acidic nature also decreases. And these are the dimers of trioxide. P4O6, AS4O6, SB4O6. Why they dimerize? It depends upon their physical state plus the stability after the combination of two molecules. Okay, so I have already told you that as the electronegativity difference between the atoms increases, acidity increases. So down the group you go, acidity decreases, right? Same logic and same order we have for pentoxides also. N2O5 is the most acidic one, P4O10, sorry. Then we have P4O10. Then we have AS4O10, SB4O10. Done. I'll write down one, order here of oxides of these elements, what all different types of oxides these elements forms. Mainly two types we have, trioxide, pentoxides, but overall, see the oxides that they form is one we have M2O3 type oxides they can form, like N2O3, P2O3 and so on. M2O4 type oxides also they form, and M2O5 types oxides also they form. Okay, so this is trioxide, this is pentoxide, right? So the oxides of this type, you see, we have N2O3, P2O3, AS2O3 and so on. N2O4, P2O4, AS2O4 and so on. Here we have N2O5, P2O5, AS2O5 and so on. Now if you compare the acidic nature, okay, so obviously when we go top to bottom, right, top to bottom if you go, right, left to right if you go, this side, okay, so what happens here, left to right if you go, acidity decreases because nitrogen, phosphorus, arsenic, like this we have. These are the oxides of same element. So we'll see the percentage oxygen character increases as we go this side down. So acidity increases. Similarly, you can write down the order of basicity also. Done. Finished, guys?
So 30 seconds.
Okay.
So could you move to the previous slide? One sec.
Previous slide.
Yes, sir.
There's a news outbreak. You heard there's a loud explosion in Bangalore.
So apparently
Yes,
there was a
sir.
jet
Sir,
or something.
towards Sajapur.
Where? What happened?
I think it was a jet or something. I'm not sure. That's what I heard.
So apparently
Jet-
HCL was up to something.
Yeah, they were test flying something.
Have you heard the loud noise or the?
Yes, sir.
I didn't hear, but everyone was speaking about it.
I got this on WhatsApp right now.
My dad thought it was a bomb.
What?
My dad thought it was a bomb. Like he thought that
Oh,
nearby.
that loud it is.
It sounded like when the transformer burst, right?
So everything is happening now only. You see, yesterday I was like in the news. It was like there was some cyclone, super cyclone, Amphan or something like that in Orissa or Bengal. So it was coming. Like today, it was going to hit the the city there, and this bomb right now, whatever bomb or jet, whatever it is, and then Corona is already in the. Everything is happening. This year is like. Okay, my brother is in Air Force. He's in Bangalore only. I have to. It's in Sarjapur, right?
So I heard it in Koramanga also.
The people in Sarjapur also reported this, I think.
Yeah.
Says here.
So I'm Sarjapur, I don't know anything.
Let it be. We can't do anything, no. So let it be. Let's go ahead. Okay. So these types of oxides order we have seen different types of oxides that forms. Okay. The nitrogen forms a number of oxides. Like few examples I have already given you: N2O, NO, N2O3. Okay. So these oxides, the structures of these oxides is important. Okay. Right. Oxidation state of nitrogen in these oxides are important. Okay. So the various types of oxides of nitrogen, you see, write down the heading. Oxides of nitrogen, we'll see the preparation method, just the reaction we'll see oxidation state and structure. Okay. So write down the heading, oxides of nitrogen. The first one we have dinitrogen monoxide. Dinitrogen monoxide. The formula for this is N2O. And N2O, we also call it as nitrous oxide. Or what is the other name? Laughing gas. Okay. The oxidation state of nitrogen is, in this oxide, is +1. Okay. It is prepared by heating ammonium nitrate, NH4NO3. If you heat at around 250 degrees Celsius, temperature is not important. It forms N2O and H2O. Right? It can also be prepared by the reaction of hydroxylamine NH2OH with HNO2, nitrous acid. What it gives? It gives N2O plus H2O. 2 molecules of H2O we get here. These are the preparation method. Right? Now, few facts for this oxide you must remember.
So what is the first point? What does it
What?
mean? What does that first point mean?
This one.
Yes, sir.
This one is oxidation state. Oxidation state of nitrogen.
Oh.
OS oxidation state is +1. Important this one, right? Oxidation state they ask in the exam.
So it looks
Okay.
like 0.5.
That's why I have corrected. Another thing is, in solid state, N2O exists in hydrated form. N2O.6H2. When you heat dinitrogen oxide, nitrous oxide at 600 degrees Celsius, it converts into N2 and 2. not that important. Okay. Now the structure of N2O, this one is important. The structure is very important here. The structure of N2O, you see, you can draw the Lewis dot structure, and it is, you can draw like this: N triple bond N and one coordinate bond to this oxygen, where this oxygen has two lone pair. There's no lone pair on nitrogen atom, and here this nitrogen has one lone pair on it. This is the structure, possible structure of N2O. Okay, or one more structure you can draw for this, that is N double bond N double bond O, and this oxygen has two lone pair, nitrogen has positive charge, and this nitrogen has two lone pair negative charge. And then after this you can take the resonating structure of this also, where this comes over here and this comes over here. So structure will be N triple bond N single bond O and one negative charge on oxygen atom and positive charge on nitrogen atom. Which of this structure is more stable?
So the first one. Right?
First one, because first one has two pi bonds. Okay, all these structures you can draw, resonating structures. Okay, can I go to the next page?
Yes, sir.
What they do, they'll ask you the, to find out the number of lone pair, bond pair of electron. Okay, in the structure, they'll ask you how many lone pairs are present into this oxides of nitrogen. So you should know the structure for that. Anyways, you can draw the Lewis dot structure. You will get the idea from that also. What is the possible structure is going to be. Second type of oxides we have, and that is nitrogen monoxide. Nitrogen monoxide. We also call it as nitric oxide. Nitric oxide, that is NO. Oxidation state of nitrogen. Oxidation state is +2. Okay, and it is prepared by the reaction of copper with nitric acid HNO3 and dilute nitric acid we are using. This is also very important. We'll see the reaction of nitric acid, okay, separately, and there we'll see when it is dilute, it gives some other oxide. When it is concentrated, it gives different oxide. When it is very dilute, it gives different oxides. So HNO3 has three different types of reaction: dilute, concentrated, and very dilute. So copper, when reacts with dilute HNO3, it gives nitric oxide, NO plus CuNO3 whole twice and H2O. This exact relation, this exact question, they ask in NEET exam once. Okay, which nitrogen oxides evolves when copper reacts with dilute HNO3? Right. So in inorganic chemistry, it is not like it is NEET questions or JEE questions. Any questions is equally important for all kind of exam. Okay, because if you know, you can do this. If you do not know, you do not know it. Okay, the portions is like this. Okay, so we'll use copper with dilute HNO3. We'll get this. We can also obtain NO, the second preparation method we have, by catalytic oxidation of HNO3. Sorry, NH3. Catalytic oxidation of NH3 gives you this. Okay, this is the preparation method we have. The structure of NO is important. Could you tell me how many electrons this NO has? NO is 8 plus 7, 15 electrons, correct? It has odd number of electron. Hence, in this molecule, we have odd electron bond present. Odd electron bond present. Odd electron bond, mainly we have two types of bond, and you have to memorize this. Where we have odd electron bond present, this you don't have to memorize. What you have to memorize is, I'm telling you, odd electron bond, we have two types. We have one electron bond, or we have three electron bond. Usually what happens in one bond, how many electrons present? Two, right? In one bond, we have two electrons. So when we have two electrons present in a bond, that bond is a complete bond, right? True bond. But when we have odd electron bond, then that bond contains either one electron or three electrons. So which one should have one electron and which one should have three electrons, that you have to memorize, right? It is given, like this molecule has one electron bond and this molecule has three electron bond. But the molecule which has odd electron bond, that you can easily understand by calculating the number of electrons. Like you see, NO has 15 electrons, which is an odd number. It means NO has odd electron bond. For odd electron bond, the bond order is half for this electron. Bond order is half for odd electron bond. Whether it is one electron or three electron bond order is half. And how do we get this idea that the molecule has an odd electron bond? Because when you calculate bond order of NO with the help of what? With the help of?
MOT.
MOT, very good. With the help of MOT, if you find out the bond order of NO, you will get this bond order as 2.5. So usually bond order means what? The number of bond presents between the two atoms in a molecule. So what is this 0.5 means? So when you get this 2.5 according to MOT, then we define this particular type of bond. That there is a molecule in which a bond called odd electron bond present, whose bond order is half, and that's why it is 2.5. So when you look at the structure of this NO, NO has 3 electron bond. And one bond is odd electron bond here, which has 3 electron present in this. So this is 1, 2, and 3 electron present over here. It is an odd electron bond. Oxygen has one lone pair and nitrogen has one lone pair. Correct? Now, these things are very important, right? Where there are two molecules, two oxides of nitrogen, where we have odd electron bond. One is this and other one is NO2. We'll discuss that later, right? So these two are the most important one out of all the oxides of nitrogen. Okay, so first thing what you have to keep in mind, that NO, obviously you don't have to memorize this, that it has an odd electron bond, because you can calculate the number of electron and you can find this out. But what you have to memorize, that this NO has 3 electron bond. So first thing is it has 3 electron bond, and since it has unpaired electron, right, it is what? It is paramagnetic in nature. This is the another thing you should know. Paramagnetic, but in gaseous state. Gaseous state, right? what happens? Write down the next thing. In solid or liquid state, it gets dimerized. And becomes diamagnetic. Done. So this property is very important. Paramagnetic in gaseous state, not always. Okay. Next, write down the third one. We have dinitrogen trioxide, N2O3 type. N2O3. What is the oxidation state here? Oxidation state is
+3.
+3. Preparation method: nitric oxide plus nitrogen dioxide combines and it forms N2O3. The another method we have AS2O3, arsenic oxide, reacts with HNO3. Again, it is dilute here, plus H2O, and it gives N2O3 plus H3ASO4. Not important. In preparation method is not important for this oxide. Okay. Write down the next property here. N2O4 in gaseous state, N2O3 in gaseous state exists as a mixture of, NO and NO2. NO and NO2. It is a blue color solution. It is a blue color solution. Next, in presence of moisture, its blue color disappears. In presence of moisture, its blue color disappears due to the formation of nitrous acid. So in presence of moisture, N2O3 combines with H2O and it forms HNO2, 2HNO2. Right? So this nitrous acid forms, hence the blue color disappears, and we also say the aqueous solution of this oxide is acidic in nature. Aqueous solution of these oxides are acidic in nature. Okay. So N2O3, the structure is this. Nitrogen attached with nitrogen is a coordinate bond and double bond O, and here also we have double bond O. This is the structure we have, where each nitrogen atom has Nitrogen atom, here we have one lone pair. Here we do not have lone pair. Two lone pair on oxygen. This oxygen has 3 lone pair. One lone pair present here. This has 2 lone pair, and that is it. Okay, so this is the structure we have. You can also draw this bond. Actually, it is a coordinate bond, right? So you can also draw the structure as this. This you can draw, or the structure you can draw like this. N single bond N. You write down one covalent bond here and a double bond here. Double bond here. So this O will have negative charge because it has 3 lone pair. This has 2 lone pair. Here we have the positive charge, no lone pair, 1 lone pair, and 2. This is the structure also you can draw. Done. Three more oxides we have here. Yeah, Advik, we'll have 3 more oxides. We'll finish this in 10 minutes. Okay, 10 minutes, we'll take a break then. Maximum 10 minutes, not more than that. Okay, we'll finish this. Okay, fourth type of oxide you write down. We have nitrogen dioxide. Nitrogen dioxide. That is NO2. NO2, the oxidation state of nitrogen is +4. It is prepared by the reaction of oxidation of NO gives NO2. It can also be prepared by the reaction of CO with HNO3. You see this reaction? We are taking here concentrated. Dilute gives you another oxide. Concentrated HNO3, if you take, it forms NO2 plus CuNO3 whole twice and H2. This is the product we get. We get 4 of HNO. So concentrated is giving you NO2. Okay. Lead nitrate, if you heat PbNO3, if you heat this, it forms PbO plus NO2 plus O. Okay. It is a strong oxidizing agent. Oxidizing agent. It oxidizes and forms higher oxides, N2O5 plus O2. Right, right. Correct, Varun. Write down NO2 is a brown gas, highly reactive and paramagnetic in nature. Brown gas, highly reactive and paramagnetic in nature. The structure you see, it also has 1 electron bond. It has odd electron bond present. Right? If you count the number of electron here in NO2, it has odd electron present, right? And 1 electron bond present onto this. 1 odd electron I can show over here. And we have 1 coordinate bond, with 3 lone pair on this oxygen. This has 1 double bond with 2 lone pair on this. This is the structure we have. Okay, so it is paramagnetic and it dimerizes into N2O4.
So, but where's the single bond? The one with only one electron?
What?
So, where's the bond with only one electron in it?
Why the bond is with only 1 electron?
So, where is that bond? So, the one which should have only one electron in it.
See, when you draw the Lewis dot structure, no? Right. So, see, there are many possibilities. Okay. Then you will get the distribution of electron is something like this. Nitrogen, oxygen, oxygen. Right. So here we have 2 electron like this, and you will get 2 electron over here. Then you will distribute electron onto this. 8, and here we have 4. 8. So 1, 2, 1, 2, 3, 4 plus 2, 6. 6, and then what we can write? We can write 1 electron present over here. Tell me how many electrons NO2 has? Valence electron.
17?
17 electron NO2 has. So how do you distribute this electron? Nitrogen, oxygen, oxygen. This is the possible distribution. 2, 4, correct? Then on the outer atom, 6, 10, 10 plus 6, 16. So if you draw this, I have directly written this structure, but when you draw this, you will have something like this. Now you try to distribute the electron. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That 1 electron which is left is present over here. So there is no possibility of forming a 3 electron bond here.
Okay.
Sometimes what happens here, with 1 lone pair, 1 unpaired electron is also present. And in that case, we can say this 3 electron moves and forms a bond over here. That is 3 electron bond. But like I said in the beginning, you should know this fact that which molecule has 1 electron bond, which one has 3 electron bond. Right. So like I said, in the first one, we have NO, the molecule is the second one, where we have 3 electron bond, and this has 1 electron, so it may form 1 electron bond over here. Right, so it has 1 electron bond. Again, if you find out the bond order of this, you will get bond order as 2.5 here also, because of 1 electron bond. So this dimerizes and forms N2O4, the oxide. It is also paramagnetic in nature. So these two oxides, NO and NO2, are very important. Okay, the structure is like this. We have the last two we'll discuss quickly. It won't take much time. We have already done the important one. Nitrogen tetraoxide, that is N2O4, dimer of the previous one. Tetraoxide N2O4. It is oxidation state is what? +4. It is prepared by cooling nitrogen dioxide, reversible. When you cool this, it converts into N2O4. Okay. Next, write down on hydrolysis it forms nitrous and nitric oxide. Okay, on hydrolysis it forms nitrous and nitric oxide. N2O4 plus H2O gives HNO2 plus HNO3. Okay, the structure of N2O4, it is the simple one, N single bond N, coordinate bond with oxygen, double bond O, coordinate bond with oxygen. Each oxygen atom has 2 lone pair. Like this. Nitrogen won't have any lone pair on this. Even this bond, coordinate bond, you can replace with a single bond like this, but nitrogen will have plus and oxygen will have negative charge in that case. Okay.
So if we put N2O4 in water, does it dissociate into NH2 plus and minus?
What? N2O4 in water?
Yeah,
it
like,
gives you HNO2 and HNO3, right?
oh, I mean, so in any solution, does it dissociate into
No,
NO2 plus and minus?
No, N2O4 won't dissociate.
Oh, okay.
N2O4 can, when you heat this, it can convert into NO2 back.
Okay, sir.
Okay, but it won't dissociate into ion. That is not possible because the bond is there covalent. Okay.
Yes, sir.
Now, last one I write down, that is dinitrogen pentoxide, N2O5. Dinitrogen pentoxide. Oxidation state, +5, and it is prepared by the reaction of P2O5 with HNO3. It forms N2O5 with HPO3. Okay, write down. Write down in solid or gaseous state. Yeah.
So what is the concentration of HNO3 here?
HNO3 concentration. We are taking here dilute acid. See, concentrated we cannot take. Somewhere in very dilute to dilute we can take. Yes, very dilute or dilute we can take. Concentrated is not useful here. Write down. In solid state, N2O5 exists as a mixture of NO2 and O2. Sorry, N2O4 and O2. Okay, in solid state, it exists as a mixture of N2O4 and O2. Next point, when it dissolves in water, it forms N2O5, dissolves in water, H2O. It forms HNO3. So first thing what we say, the aqueous solution of this oxide is acidic. Aqueous solution of this oxide is acidic. And N2O5 is also known as anhydride of HNO3. N2O5 is also known as anhydride of HNO3. correct, and I dry it off HNO3. And the structure of this, you see, it is N, one oxygen atom bonded between the two nitrogen atom, double bond O, double bond O, and one coordinate bond. Again, I am telling you this, if you see this kind of bond in the book, that is also right. Okay, it is not wrong. Okay, both way you can represent. But charge must be there. Okay, oxygen atom has two lone pair. Here also we have two lone pair. There is a NON bond into this. Okay, so they can ask you this question also, in which of these oxides, which of the oxides of nitrogen there is NON bond present. So this bond is present in N2O5. Okay. Okay guys, we'll take a break now. Okay, after the break we'll see some other compounds of these elements. Okay, we'll start with halides after the break. Take a break now. We'll resume the class at 4:45. Hello.
Yes,
Yeah.
sir.
Yeah. So we have discussed the oxides of nitrogen. Next, so hydrides, oxides we have discussed. Next, the third type of compounds which these elements forms, write down, that is halides. Okay. Okay, write down. The elements of group 15 the elements of group 15 form two types of halide. One is trihalide, and other one is pentahalides. Okay, trihalides of MX3 type. Okay, in this, like I said, nitrogen cannot form pentahalides due to unavailability of d orbital. Okay, how do we prepare trihalide? By direct reaction of elements with halogen X2. Limited supply of this. Okay, or if this is limited, or we can say this metal is in excess. So this gives you MX3. If it is excess, then pentahalides forms. Okay, structure again it is similar to that. Two hydrides, one lone pair, and 3 bond pair like this. Structure is exactly same. The element is sp3 hybridized with one lone pair and 3 bond pair. Okay, write down the bond angle of trihalides increases with increase in electronegativity.
So can you repeat it once more?
Yeah, the bond angle of trihalides increases with increase in electronegativity of halogen atom. This is just reverse of the bond angle of hydrides. Okay, so if you have suppose piece F3, then PCl3, PBr3 and PI3. The bond angle we have maximum for PI3 because the outer element, if electronegativity increases, electrons goes apart, like far away from each other, and hence this bond angle decreases. Right, so this is one thing. Next point you write down, all trihalides are predominantly covalent. All trihalides are predominantly covalent. Comma, as we go down the group, the ionic character increases. As we go down the group, the ionic character increases. Like for example, BiF3 is ionic in nature, but other trihalides of bismuth is covalent. Okay, mostly covalent, partially ionic it is. Write down. Among all trihalides of nitrogen, among all trihalides of nitrogen, Ni3 is the least stable. Ni3 is the least stable. The reason is that same only. Down the group you are going, the stability decreases because of increase in bond length. If I talk about the Lewis basicity of NF3, NCl3, NBr3, and Ni3, which one is the most basic?
So is it Ni3?
Ni3. Why it is basic?
So otherwise the electronegativity will pull the electron, so it can't release it for fluorine.
Correct. As electronegativity decreases, tendency to lose electron will be more, and hence the Lewis basic nature increases. Okay, write down. These trihalides goes under hydrolysis, and forms corresponding hydrides. Hydride. This is for nitrogen, okay? And correspond. These trihalides, nitrogen trihalides, goes under hydrolysis and forms hydrides. Okay. But in this, what happens? NF3 does not go under hydrolysis. For NF3, we have no hydrolysis because of strong bond. But all other halides goes under hydrolysis. For example, NCl3 reacts with water, it forms NH3 plus HOCl, hypochlorite. Okay, it does not react with NF3 does not go under hydrolysis because of strong bond of nitrogen and fluorine. Okay, PCl3 hydrolysis, you see, PCl3 goes under hydrolysis and forms H3PO3. H3PO3 plus HCl. Okay. Next one, I write down. The second type of halide we have, that is pentahalide. Nitrogen does not form this halide. Discussed this many times. Okay. Write down except nitrogen. Except nitrogen, all other elements forms pentahalides. forms pentahalides. Next, write down phosphorus pentachloride, that is PCl5. Phosphorus pentachloride is prepared by the reaction of white phosphorus with excess of dry chlorine. Okay, so one of the method is what? White phosphorus P4 and reacts with Cl2 gas. Excess of this. Right, you'll first get PCl3 and then you'll get PCl5. Okay. We can also take phosphorus trichloride for the preparation of chlorine, PCl5. Right, this is how pentachloride, phosphorus pentachloride forms. Right, so mainly we use white phosphorus in all these, that you must remember. This is white phosphorus. This white phosphorus we can also use with sulfuryl chloride in order to prepare phosphorus pentachloride. Sulfuryl chloride is SO2Cl2 and it gives PCl5 plus sulfur dioxide SO2. No, this is solid, it's not gas. PCl5 exists in solid form.
So what do you mean by white?
White phosphorus it is. It is the allotrope of phosphorus. Okay, we'll discuss that. There are 5-6 allotropes of phosphorus we have. We'll discuss that in phosphorus. Okay, white phosphorus we have red phosphorus, black phosphorus, alpha black, beta black phosphorus. All these are different forms of phosphorus. Okay, we'll discuss that in phosphorus.
Yes.
Okay, so and this is important. Why? Because it asks in the exam that which phosphorus we use, white or red. Okay, so this is the white phosphorus we are using here. Okay, write down next point. Write down pentahalides. Pentahalides are thermally less stable. Than trihalides. And it dissociates into trihalide on heating. Trihalide on heating. So phosphorus pentachloride PCl5 that you have, its structure is trigonal bipyramidal. Okay, and that structure is this. Phosphorus, we have chlorine on the top, chlorine on the bottom, and chlorine, this is phosphorus pentachloride, correct? We know this is what? This is axial bond and this is equatorial bond. This is axial and this is equatorial. Okay, so axial bonds are weaker than equatorial bond. That's why when you heat this, these two bonds dissociates, and PCl5 can easily convert into PCl3 plus Cl2. Okay.
So could you repeat?
See, the structure of PCl5 is this phosphorus pentachloride,
Yes, sir.
trigonal pyramidal. Okay, so this two bond, we have two types of bond here, right?
Yes, sir.
One is equatorial bond. This bond, and this bond are three equatorial bond we have. This bond and this bond are two axial bond, right? So
Yes, sir.
axial bond length is more than to that of equatorial. Okay,
Yes,
and
sir.
that's why axial bond is weaker than the equatorial bond we have. Hence, if you heat this, then these two bonds can easily dissociate, and the two chlorine atom comes out and forms PCl3.
Yes, sir.
Right. So that's why this kind of reaction is possible when you heat this. Why it forms Cl2? Because of the two axial bond, weaker bond can dissociate easily.
Okay, sir.
Right. This PCl5 is what? It is a yellow crystalline solid. Crystalline solid. Write down, in moist air, it first hydrolyzed into POCl3. In moist air, it first hydrolyzed into POCl3, which then converts further into H3PO4, orthophosphoric acid. POCl3 plus HCl it forms, and then again this POCl3 reacts with water, forms H3PO4 and HCl it forms. Okay, so if you use direct here, if you write down excess of H2O, PCl5 plus excess of H2O, your product will be this and this. One step also you can write down this way. Okay. Now these reactions we all know that PCl5 converts carboxylic acid into acid chloride. Okay, it replaces hydroxy group, right? So this kind of reaction you see, we must have done this in organic chemistry. Like PCl5 reacts with CS3COOH. What is the product we get? We get CS3COCl plus H3PO4 plus HCl. Okay. Now one last thing here, in solid state, PCl5 exists as dimer in ionic form. Exists as dimer in ionic form. Okay. So this PCl5 exists as P2O10 in dimer form, and this has two different parts. The structure of this has two different parts. One is tetrahedral unit, and other one is octahedral unit. Octahedral unit. You see this structure? The tetrahedral unit is the cationic part we have. So phosphorus has 4 chlorine atom attached like this tetrahedrally. Cationic form, and then we have octahedral unit anionic form is this phosphorus, chlorine, 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 and the top we have chlorine, and on the bottom we have this is negative charge. Okay, so like I said, it has 2 different units in solid form. One is tetrahedral, one is octahedral. This tetrahedral unit, we know it is sp3 hybridized, and this one is sp3 D2 hybridization. Done. Okay, so we are done with all the compounds that it forms, their preparation and properties. Now we are left with nitrogen, its preparation and properties, phosphorus, preparation and properties, and in the last we have to discuss the oxy acids of phosphorus. Okay, just we need to know the structure of those oxy acids of phosphorus. Okay,
So,
right, yeah.
So in that reaction with PCl5, so won't we form POCl3, the organic reaction?
Which one?
So the one with, yeah, so with the acid, so won't it form POCl3?
Further it forms, this reacts with water again, and then it forms POCl3 and H2O.
Oh, okay, sir.
Okay. So write down the last 3 things we are left with. Nitrogen, we'll see its preparation and properties. First of all, you see nitrogen is, we all know, it is a diatomic molecule. It has capability of to form multiple bond, okay, exist as N triple bond N, which each nitrogen atom has one lone pair. Why it forms multiple bond? Because the small size of nitrogen, the 2 nitrogen atom which has the orbital unpaired electron present in the 3 orbitals of nitrogen, and the size is small, so all the 3 orbitals are pretty close enough so that they can lateral overlap is possible over there, and hence it forms multiple bond. Okay, it is a diatomic molecule. Okay, how do we prepare this? Okay, write down on a commercial scale. First method, preparation, write down. Write down on a commercial scale, it is prepared by fractional distillation of air. Okay, so this term you must remember, fractional distillation we use for commercial purpose. Okay, distillation is again a method by which we can separate the component of a mixture based on their boiling point. Okay, if we have 2-3 different components present in a mixture, with different boiling point. Then with distillation, we can separate that mixture. Okay. In detail, we don't have to study. It's not there in our syllabus, but in solution chapter, we'll discuss a little bit about it, right? This particular method. So fractional distillation we use over here for commercial preparation of nitrogen. Second point to write down, laboratory method. The second one is laboratory method. Write down. It is prepared by heating a mixture of NH4Cl and NaNO2, ammonium chloride and sodium nitrite TE, prepared by the mixture of ammonium chloride with sodium nitrite. Okay, so the reaction is this, you see, NH4Cl plus NaNO2 aqueous. This is also aqueous. Now when you heat this, it forms NH4NO2 plus NaCl. First step is this, NH4NO2. NH4NO2, further you heat this. So it is a double decomposition reaction. First is this, second is this. Further you heat this, it gives N2 and H2O goes out. Right, in this reaction what happens, in a small amount NO and HNO3 also forms. First of all, you write down this reaction, then I'll dictate you this. Write down, in this reaction, a small amount of NO and HNO3 also forms as impurities, which can be removed
Could you repeat it?
in this reaction. A small amount of NO and HNO3 also forms as impurities, which can be removed by passing passing the gas through aqueous sulfuric acid containing K2Cr2O7.
Passing gas through
Aqueous sulfuric acid containing K2Cr2O7. This is the one way by which we can prepare N2. Another way is we can heat ammonium dichromate, that is NH4 whole twice Cr2O7. Ammonium dichromate you heat and will get N2, H2 and Cr2O3. Right, this is chromic oxide, Cr2O3. This fourth reaction, and all these are, see, the first one is fractional distillation, and whatever this we are discussing, it comes under laboratory preparation. All these methods we can use. Okay, we can also use thermal decomposition of sodium or barium azide. Okay, so NaN3, this one is the most important one. NaN3, if you heat, it gives Na plus N2. Barium azide is sodium azide. Barium azide is BaN3 whole twice. When you heat this, it forms Ba plus 3N2. By this method, the nitrogen that is obtained here, right, it is the purest form. Whatever the method we have done, this method gives you the pure form of nitrogen. And that's why these two are very important. They've asked this question also. Okay, write down the properties. It is colorless, odorless, tasteless gas. Due to high bond strength and triple bond end, due to high bond strength, its reactivity is very less. Okay, high bond strength, reactivity is very less, but as temperature increases, reactivity increases. Okay, next write down. Nitrogen reacts with active metals like Li, Mg, Ca, etc. Nitrogen reacts with active metals like Li, Mg, Ca, etc. at high temperature and forms nitrides. So you see the reactivity of nitrogen is very low because of the high bond strength of nitrogen atom. That's why most of the reaction of nitrogen takes place at high temperature. Right, so reaction with metals is important. Li plus N2. When you heat this at high temperature, it forms 2Li3N, lithium nitride. When you have magnesium plus N2, it forms Mg3N2, okay, magnesium nitride. So it forms nitride on reaction with metals, active metals. Next point, with non-metals, write down with non-metals, it forms covalent nitrides. Right, covalent nitrides. For example, N2 plus H2 gives NH3, N2 plus O2 gives NO. All these are covalent compounds. Okay, with non-metals, it gives covalent compound.
So can you go back to the last slide for 1 minute? Yes, sir, thanks.
Okay, this one is also important. Write down, it reacts with calcium carbide, CaC2 with N2. It forms, on heating, it forms CaCN2 plus carbon. This compound is calcium cyanamide, and this mixture they have asked many times in the exam. This mixture we call it as nitrolim, Nitrolim, nitrolim. Okay, Okay. This CaCN2, when you dissolve this in water on hydrolysis, CaCN2 on hydrolysis gives CaCO3 plus NH3, ammonia. Right, so ammonia is used as a fertilizer, right? That's why we also use this nitrolim, right, for the fertilizer purpose, right? For no, in fertilizing industry we use nitrolim also. So, however, nitrolim is a mixture of CaCN2 plus carbon, but we can also consider this nitrolim as a fertilizer, right? CaCN2 gives NH3. Okay, these are the few reactions of a nitrogen that we have done. Now, the another one you write down, one compound of nitrogen we are left with, very important compound, and that is nitric acid. HNO3. We all know it is a very strong acid. Write down. Write down, in lab it is prepared by, in lab it is prepared by heating KNO3 or NaNO3 with concentrated H2SO4. Right, so we have NaNO3 with H2SO4 concentrated. Right, it gives NaHSO4 plus HNO3. So here this H2SO4 is behaving as a monobasic acid, right? NaHSO4 and HNO3. Okay, this is the laboratory preparation method. Okay, next write down, on commercial scale it is prepared by Ostwald's process. On commercial scale it is prepared by Ostwald's process. Okay, what is Ostwald process? Write down. It is based upon the catalytic oxidation of ammonia by atmospheric oxygen. Okay, so in the first step what we do, we are using ammonia for the preparation of HNO3 on commercial scale. So what you do here, first step, we have ammonia, so 4 molecules of
Wait, so could you
NH3.
repeat that previous one?
Ostwald process, write down. This method is based upon the catalytic oxidation of ammonia by atmospheric oxygen. Catalytic oxidation of ammonia by atmospheric oxygen. So 4 molecules of NH3 oxidized by the atmospheric oxygen gas in presence of platinum catalyst. We can take platinum as a catalyst, rhodium also we can take as a catalyst, and it forms NO first, nitric oxide, and H2O. NO and H2O, we both get in vapor form, gaseous form, because the temperature here it is very high, around 500 Kelvin we use this temperature. Okay. Now this NO in the second step, it again combines with the atmospheric oxygen, right, and converts into nitrogen dioxide. Second step, this happens. NO2, right? NO2 gas we get here. NO2. Now after this, the hydrolysis of nitrogen dioxide, right, H2O liquid gives you HNO3, aqueous, and nitric oxide gas also forms. So this is the commercial method of preparation we have. Okay, one more thing here, it is what? This nitric oxide and this aqueous HNO3, this mixture that we are getting here finally, aqueous HNO3, right? This mixture is concentrated by distillation to give 68% of HNO3. Means after this, we'll do the concentration of it, right? Means removal of NO, because NO is present as an impurity over here, right? So we have to remove this NO. So for that, we'll do the concentration here of this mixture, and that gives 68% pure HNO3. Right. This mixture, the aqueous HNO3, one term we are going to use over here, which you haven't studied yet. We'll discuss this term also later on. That this HNO3 and water, this mixture forms an azeotrope here. Right, an azeotrope. This mixture will be an azeotropic mixture, not related to this particular method of preparation, but this information you should have. Azeotropic mixture when HNO3 is 68% and H2O here is 32% by mass. 68% by mass, 32% by mass. This azeotropic mixture means what? We'll discuss this topic in solution chapter, but again, azeotropic mixture, I'll tell you what, for any mixture, right, whatever component is present into that, you will have a fixed composition where the separation of the two component is difficult, is not possible. Because at a fixed composition, the boiling point of this and this becomes equal, right? And since the boiling point is same at this particular composition, hence separation by distillation is not possible, right? So that mixture where the components will have a common boiling point, that particular composition, we call it as azeotropic mixture. Okay, just the definition of this, even this thing is also not in details we have in this in our syllabus, right? But sometimes in JEE they have asked this question, that which of this mixture forms an azeotropic mixture, and the only way you can do this by memorizing this. There is no other way you can find out this particular percentage, like at this level. Okay, you have this calculation there in that master's and graduation level, but till now, here in the syllabus of 11th and 12th grade, you don't have this calculation part. So you should know which all mixture can form azeotropic mixture. There are 5-6 examples, not more than that. Okay, we'll discuss that into this thing, solution chapter. Okay, composition you have to keep in mind. Okay, a structure of HNO3 is what? Could you tell me? The structure of HNO3 is this: N double bond O, single bond O, OH. Where here we have 3 lone pair, 1 negative charge. Nitrogen has 1 positive charge. Oxygen has 2 lone pair. Here also we have 2. This is the structure of HNO3. 1 hydrogen present here, so it is monobasic acid. Oxidation state of nitrogen. Oxidation state of nitrogen.
+4.
Right? Two, 3, 4, -1. H2, HNO3 we have, no, +5. Okay. -2, +2, +1, +1, +4 and +1 already there.
So
+5 it is. Oxidation state is +5. Right now, next. It is a colorless liquid, have pungent odor. Okay, next line. Aqueous solution of HNO3 is yellow due to dissolved NO2. Okay, due to dissolved NO2, it appears to be in yellow color, right? So this pure HNO3 and NO2, this mixture that we have, nitrogen dioxide, this mixture we call it as fuming nitric acid. Fuming nitric acid.
So what's written below HNO3?
Pure form of it.
Oh,
pure
pure.
HNO3, yeah. Next point, write down. In presence of light, it decomposes and gives nitrogen dioxide. See, all the reactions of HNO3 in which the oxides of nitrogen we are getting, all reactions of HNO3 in which the oxides of nitrogen we are getting are important. They'll ask this question, like one example if I give you, in presence of light, HNO3 decomposes and gives NO2. So they can ask you this question, that in presence of light or photochemical decomposition of HNO3 gives you what gas? And they'll give you 4 options of oxides of nitrogen. Right? So oxides of nitrogen, wherever you are getting, you have to be very careful. You must keep that in mind. So write down the first point. In presence of light, HNO3 decomposes and gives nitrogen dioxide gas. Done. So what is the reaction we have? We'll see all the reactions of HNO3. You won't get more than this anywhere. Okay, if you get one or two here and there, you can keep that in mind. But this is sufficient, you can say. So if you have 2 moles of HNO3 in presence of light, it decomposes into 2NO2 plus H2O plus 3 by 2 O2. 1 by 2, 3 by 2 O2. We have 6, no, so 3. I think it's 1 by 2 it should be. This is the reaction we have. And that is why, to prevent this decomposition, this HNO3 is stored in brown color bottle. Brown colored bottle. It is stored in brown colored bottle. Okay. Now we'll see the different reactions of HNO3 with various different concentration and gives you what gas here. Okay. So the first reaction we are going to see here, reaction with concentrated HNO3. First one you write down. Write down the metals like Cu, Ag, Hg, Pb, zinc reacts with concentrated HNO3. Concentrated HNO3 gives you metal nitrate, and nitrogen dioxide gas evolves. And whatever reaction we are going to do now, after this, in all the reactions except only one reaction, in all the reactions, water we always eliminate, which is not important. But in order to understand the possible product, one thing is always water, that is for sure. Okay, so all these metals with conc HNO3 gives you nitrogen dioxide. I'm not writing down the entire reaction because it takes so much of time, right? So copper with HNO3, what it gives? Copper nitrate. What is the formula for copper nitrate? CuNO3 whole twice plus NO2 plus H2O. That is the product. AgNO3, HgNO3. Right? Like this, we can write down the formula metal nitrate and you will get the product. But they won't ask you what is the product you get in this reaction. Like I said, they'll ask you this plus this gives you what nitrogen gas. So NO2 gas evolves into this one. Okay, this is one. Okay. Second point in this, we are talking about concentrated only. Second point, write down iron, Fe, aluminium, cobalt, nickel, and chromium, these metals, becomes passive with concentrated HNO3. Becomes passive with concentrated HNO3.
So what is the last metal?
Chromium, chromium.
Oh.
Actually, what happens, all these metals forms a thin layer of oxides on its surface. Initially, that oxide forms, and because of that oxide layer, HNO3 further cannot attack onto the metal atom. That's why the reaction is not possible. So it rendered passive with concentrated HNO3. Okay, so I have write down here concentrated HNO3. It becomes passive. Why it becomes passive? Because of the formation of oxide layer of this. Okay, oxide layer formation. Whenever you have this in inorganic chemistry, that reaction is not taking place. 80 to 90% of the cases is this formation of oxide layer on this surface, and hence the reaction further is not possible. Okay. Okay, if you have ferric nitrate, right, Fe2 plus ion, if you have ferric nitrate, this on reaction with HNO3, I'll write down this way. Fe on reaction with HNO3 in presence of acid, if you are taking suppose H2SO4, okay, concentrated, not very high concentrated, moderate concentration you can take for H2SO4, then it converts into Fe3O4, Fe3 plus, but still the important thing is what nitrogen gas is getting evolved, that is NO2 only here. In all these cases, nitrogen dioxide gas evolves, right?
So is HNO3 dilute over here?
It is concentrated only. All these three reactions is for concentrated HNO3. Okay, so concentrated HNO3 gives you NO2. I have given this a separate thing because it becomes passive, no reaction here. Okay, now the next one, write down reaction with dilute HNO3. Now you see, and you compare this with the first reaction that we did in concentrated one. If you have metal like Cu, Ag, Hg, Pb, all these metals are there also, reacts with dilute HNO3, then again we'll get metal nitrate, which is common. We'll get metal nitrate, but the oxide of nitrogen is different. We are getting here nitric oxide, and like I said, H2O will always get evolved into this. It is not nitrogen dioxide, but it is nitric oxide, that is NO. In this, if you are taking zinc, if you are taking iron, if you are taking tin with dilute HNO3, then again it forms metal nitrate, and the gas evolves over here is N2O, dinitrogen oxide. H2O will always be there. You see, everything is same, so there's no other way you have to memorize this. Okay, nitrogen, dinitrogen oxide is getting evolved over here. Done. Okay, so these two reactions are there when dilute HNO3. Next, write down reaction with very dilute HNO3. In this case, the first case, metals like magnesium, manganese with very dilute HNO3, it evolves hydrogen gas. Obviously, we'll get nitrate, metal nitrate here, but it evolves hydrogen gas. And in this reaction only, H2O does not come out. Okay, H2 gas evolved into this one. Okay. Next, write down non-metals like carbon, sulfur, non-metals like carbon, sulfur does not react with dilute HNO3. Carbon, sulfur does not react with dilute HNO3, but with concentrated HNO3, it gets oxidized and evolve NO2 gas, nitrogen dioxide.
So could you repeat the start of that point? The
Okay. Non-metals like carbon, sulfur, iodine, many we have non-metals, does not react with
yes, sir. After that one, only the metal, non-metal.
does not react with dilute HNO3, but with concentrated at HNO3, it gets oxidized and evolves NO2 gas. And water will be there always, right? So these are the reactions for HNO3 that you must remember. Okay, this part, this dilute, very dilute, concentrated, what nitrogen gas is getting involved is very important. Okay, next, the last part of this chapter is,
Could you go to the previous slide?
just a second.
Okay, sir.
All these reactions and the content that we have covered today, this much is not given in NCERT. Okay, if you want to read all these, you have to get some other book. Okay, it will be there in the other book. But yes, NCERT, all these things are not given. But I will suggest you first you finish NCERT properly. Okay, that you must do. Okay, now the next thing we have to start with is phosphorus. Okay, the last part, phosphorus, we have already discussed the phosphine preparation properties, other things we have discussed in phosphorus. Okay, now we are left with only few allotropes of phosphorus, its preparation properties, and oxo acids of phosphorus. All those S3PO3, S3PO4, those structures and basicity of phosphorus. Okay, Now you see allotrope, phosphorus, if you talk about, phosphorus has various allotropic forms. Okay, so it has, write down, it has 3 allotropic forms. 3 allotropic forms. The first one is white, or we also call it as yellow. White yellow phosphorus. Actually, the color is white when it forms. Its color is white, but then it reacts with atmospheric oxygen and forms a red color oxide layer on its surface. So that red color plus white color already it has initially. So that combination gives you, and it starts appearing as yellow. That's why it is yellow phosphorus also. So basically those things are not important. The only thing you have to keep in mind that white and yellow phosphorus are the same thing. Okay. Next one we have red phosphorus. Is it? I think this white plus red appears to be yellow, I guess. This is what I remember. Means it not exactly yellow, but it appears like yellow, I think. And that is the reason it is said to be yellow phosphorus, white and yellow. Anyways, we'll see this here, right? We'll see this. The reason for this white is called as yellow phosphorus because it forms a red colored oxide layer, and then this red and white color which already have, it appears to be yellowish. That's why we call it yellow phosphorus, but we'll cross check this one. Let it be. Okay, red phosphorus this, and yeah, and the other one is black phosphorus. Black phosphorus. It is the least important. The most important one we have here, white phosphorus. Okay, we'll finish this black phosphorus. Black phosphorus, it is also classified into 2 categories. Next, okay, black phosphorus also classified into 2 categories. One is alpha black phosphorus and other one is beta black phosphorus. Alpha black and beta black phosphorus. Okay, this alpha black phosphorus is obtained by red phosphorus. So when we have red phosphorus, red P, and you heat this at around 453 Kelvin, this convert into alpha black. Alpha black. Alpha black phosphorus, we also call it as orthorhombic. Orthorhombic. Yes, correct, Param. We also call it as orthorhombic. Just a second. Alpha black is not orthorhombic, I guess. It is one correction you do. It is not orthorhombic. Orthorhombic is beta black actually. Beta black, we also call it as orthorhombic. Same thing. Okay. It's not P8, it's P4, and I'll discuss the structure. Actually, the exact structure is not defined. Okay. Beta black phosphorus has graphite-like structures. Okay. This has tetrahedral structure and this has tetrahedral unit but polymeric structure. We'll talk about it. Exact structure is not yet known. Okay. Still the research study is going on. First, let me finish this. Alpha black obtained from red phosphorus. We heat this, we'll get alpha black phosphorus. Okay. Beta black phosphorus can be obtained from white phosphorus. So you have white phosphorus, and when you heat this around 473 Kelvin at very high pressure, almost around 10,000 atm, right? 10,000 atm we use. 4,000 to 10,000 basically we use.
So how do they even measure that kind of thing?
Right? Sorry?
So how do they even measure that kind of pressure?
We have pressure gauge, no? We required, since the pressure is very huge, so we also required, normal pressure gauge obviously we cannot use because at that pressure it cannot sustain, right? But yes, obviously, whenever you have to measure the pressure, you have to use pressure gauge for this thing. There are different pressure gauge which we can design for this kind of purpose, which can sustain those high pressure actually. Okay, it is very difficult to measure those at that high pressure actually. So white phosphorus heat at this temperature around 1000 atmospheric, 10,000 atmospheric, and it gives beta black phosphorus. Beta black phosphorus. Okay, in beta black phosphorus, 2-3 points you must remember. It has a layered structure. Write down, like we have in graphite. Layered structure it has, in which each phosphorus atom is covalently bonded. Each phosphorus atom is covalently bonded to 3 neighboring phosphorus atoms. Okay, it has layered structure in which each phosphorus atom is covalently bonded to 3 neighboring phosphorus atoms. Okay, the structure of beta black phosphorus is similar to that of graphite. Okay, similar to that of graphite. Okay, so this is it. Beta black is not that important. This is it we have here. White yellow phosphorus, I'll just discuss, write down the structure, draw the structure over here. It has tetrahedral unit of 4 phosphorus atom presently. Tetrahedral unit like this. Okay, of phosphorus atom. Okay, bond angle is 60 degree. Not that important, but bond angle is 60 degree. No, it is not conducting actually. Phosphorus is not conducting. Slippery tendency is there, but it is not that great. Okay, it is not conducting like graphite, just has similar structure. Okay, it has no unpaired electron, hence it is not a conductor. Okay, so this is white phosphorus, the structure is this. Red phosphorus, it has a polymeric structure of P4 unit. I'll show you how this structure is. Proposed structure is this, it is not yet confirmed. We have 4 phosphorus atom attached like this. And this is further connect with the another unit, which is this. And so on. It goes like this only. So this is red phosphorus actually. This is red phosphorus. This is white phosphorus, and it has this thing, graphite-like structure. Okay, so this is it for today. We are left with some preparation method of white phosphorus, preparation and properties, and then the last part, that is oxo acids of phosphorus. Okay, so we have done a lot today. Next class we'll finish this in half an hour, and then we'll move on to the group 16. Okay, group 16 elements. Okay guys, thank you. I have uploaded the assignment on Learnist. Okay, so you can solve those assignment, and we'll share some more PDF, advanced level PDF for this chapter. Okay, on the group. Right?
Thank you, sir.
Thank
you, sir.
Thank you,
sir. Thank you, sir.
guys. Take care. Bye bye.